Well, hello, this is Dr. Jack Jackson, and this video we're going to start talking about some transformations in earnest now. Um, we've done some preliminary work, just a few beginning things in this playlist, and then we talked a little bit about vectors. We're going to need vectors to help us define the first kind of transformation we're going to look at, which is a translation. So we'll get to that in a bit, but first let's talk about what do we mean by transformation anyway. So formally, the definition is a transformation of a Euclidean plane is a bijection, that's a one-to-one onto mapping of that single Euclidean plane back onto the same Euclidean plane. So it takes a point in the domain, which is in the plane, and it sends it to another point in the plane, maybe the same point, maybe a different point. A point in the domain is called a preimage point, and the corresponding output point under the transformation is called its image. And sometimes we refer to a set of points, like a geometric figure, like a triangle, for example, as a preimage set, and all the images of these points is its corresponding image set. And sometimes we just drop the word set from these descriptions. So we talk about a preimage being maybe just a figure like a circle or a triangle or a quadrilateral of some kind, and then we have its corresponding image set. And so for these notes, we're going to restrict the word transformation to indicate a transformation of a Euclidean plane. However, there are certainly other versions of transformations, for example, 3D transformations and others that we could look at. So a transformation is really a set of ordered pairs, preimage and image, where every preimage and image pair are both points in the Euclidean plane. And notice that there's a one-to-one correspondence, a bijection between the points in the plane and their Cartesian coordinates. So you can map the plane to the, ordered pairs of real numbers. This is what we mean by this, R cross R. And therefore, we can equivalently think of a transformation as a set of ordered pairs of real numbers. So notice that technically both the domain and range of a transformation are the entire plane. However, we will often be concerned with the action of the transformation on a subset of the points in planes, like on a specific geometric figure, such as maybe a triangle. In fact, a lot of times we'll be looking at what it does to a triangle. And thus we can view a transformation as a function which takes a geometric figure, a single point, a set of points, a triangle, a graph of a relation, something like that, called the preimage set, and produces um, as an output another geometric figure called the image set. Okay, so notice that since a transformation is a function, every preimage point is mapped to exactly one image point in the plane. And since a transformation is injective, remember injective means, another word for injective, of course, is one to one. Every image point has only one preimage. And since it's surjective, okay, onto the entire plane, every point in the plane has a preimage, and every point in the plane is a preimage and has a preimage. All right, so now a fixed point of a transformation is a point which is its own image. It's a point that doesn't move. So a fixed point is a point where the preimage point equals the image point, so it's a point that's left alone or fixed by the transformation. The identity transformation is a special transformation which fixes every point of the plane. So the identity transformation is really the do-nothing function that leaves everything alone, mapping every point right back to itself. Absolutely nothing moves. A continuous transformation is a transformation which is a continuous function. So what does that mean? Well, a transformation, say T mapping P to P, where P is a Euclidean plane, is continuous at a point A in the plane if and only if for every epsilon greater than 0 there exists a delta greater than 0, such that if B is a point in the plane such that the distance from A to B is less than delta, then the distance from the images T of A to T of B is less than epsilon. So I'm not going to belabor this point, but this is very similar to the definition of continuity that you may have studied in a calculus class if you've taken a calculus class. And a continuous transformation is a transformation which is continuous at every point of the plane. Now, a linear transformation is a continuous transformation which preserves linearity. In other words, a continuous transformation is a linear transformation if and only if getting any two distinct points A and B in the domain plane, then the line segment with these endpoints, the line segment AB, is mapped to the line segment whose endpoints are the image points T of A and T of B. So the line segment AB maps to the line segment T of A, T of B. So T of A is an endpoint. It's going to be mapped to an endpoint here. T of B is mapped to there. And any points between A and B will be mapped to points between T of A and T of B. And furthermore, the image set of the unique line containing AB is the unique line containing the image point T of A and T of B. Okay. All transformations in these notes in this chapter are going to be linear transformations. Okay, so they all are going to have this property. All right, how about a couple of more definitions here to get us going? A conformal transformation is a mapping which preserves angle measure. In other words, it's a transformation T is conformal if and only if given any set of three non-collinear points A, B, and C in the domain plane. Of course, we know we can make an angle ABC right out of that, right? Then the measure of the image angle, angle T of A, T of B, T of C, is the same as the measure of the pre-image angle ABC. So when you map an angle, angles get mapped to angles, and they do it in such a way that the angle measure stays the same between the pre-image and the image point. Okay? That's conformal mapping. An isometry, or also known as a rigid transformation, is a transformation that preserves distance measure. Okay, the word iso means same and metry means measure. Isometry literally means same measure. This way they're talking about the measure of the length. Okay, so an isometry is a transformation that preserves distance measure. What does that mean? It means a transformation is an isometry if and only if for any pair of distinct points A and B in the domain plane, the distance between their image points, T of A and T of B, is equal to the distance between the image points A, B. Okay, so isometry preserves distance, conformal mapping preserves angle measure. Now, so far in our study, the way we've been doing it in my class, when we've been talking about congruence, we've kind of done it in a real ad hoc way, right? We've done it in such a way that we're talking about congruence of line segments first, just saying they had the same measure. Two angles were congruent if and only if they had the same measure. Then we had triangles, meaning the lengths of all the sides, corresponding sides were congruent, and the corresponding interior angles were congruent. Then we talked about talk about quadrilateral congruence a little bit, and circles congruent if they had the same radius, and so forth. So we kind of did this kind of on an ad hoc way of just defining congruence, figure by some very special types of geometric figures. We're getting ready in this little section here to talk about defining congruence in a very general way. So we'll get there in just a little bit. Unless otherwise stated as an exercise, we will assume that we have all the postulates, definitions, and propositions we have developed for Euclidean geometry thus far. And of course, we were in Euclidean geometry only. Now, here is an interesting exercise here that is one of the few proofs in this particular section of the notes, this chapter. See if you can prove these. If T is an isometry, then T is a linear transformation. Right? So basically what do you have to prove there? You have to prove that if T preserves distance measure, then a line segment will be mapped to another line segment. Really, that will take care of it. So then lines will be mapped to lines. If T is an isometry, then T maps any triangle to a congruent triangle. Okay, so you want to see if you can prove that if it preserves distance measure, it's going to have to preserve angle measure. Maybe you can think about what do we know about triangles, about links. If we lock down all three links, what happens? You're going to lock down the angles too. So the side triangle congruence theorem is going to be a big step in that proof. Proposition 1c, if T is an isometry, then T is conformal. That basically is the same as B, right? Showing that if it's isometry, then it must map angles to congruent angles. If it's an isometry, then T maps any circle to a congruent circle. That one is pretty straightforward. And E, a transformation is an isometry if and only if it maps line segments, circles, angles, triangles, and quadrilaterals to congruent image sets. So line segment to a congruent line segment, circle to congruent circle, angle to congruent angle, triangle to congruent triangle, and quadrilateral to congruent image quadrilateral. Really, if you've done parts A through D, you've already proved all of that except for the quadrilateral part. So once again, up to this point, we define congruence of figures in a real ad hoc manner, only defining congruence for line segments, circles, angles, triangles, and quadrilaterals. But we can do a much more general approach, would be able to use isometries to define congruence. And this is very consistent with Euclid's notion of superposition. He clearly talked about the idea of superposition of congruent figures, which is basically equivalent to finding an isometry mapping a pre-image figure to a congruent image figure. And this leads us to the following general definition. Two geometric figures are congruent if and only if there exists an isometry mapping one figure to the other. Now that is going to be our overall definition of what it means to be congruent. Now, of course, for this to make sense, it has to be consistent with our earlier definitions. So then we need to prove that that we're not having two different meanings of congruent for triangle, for example. Okay, and so up here, once we prove once we prove this theorem up here, this proposition 1 up here, okay, our transformation proposition 1, this proposition there is going to tell us that that isometries do map a congruent triangle to a triangle to a congruent triangle. It's going to tell us that it does map lines to lines and line segments to line segments. It tells us that it's going to map angles to congruent angles, circles to congruent circles, triangles to congruent triangles, line segments to congruent line segments. Okay. And so in that sense, we can see that this is going to be okay, at least in terms of those figures, and then it just opens up the idea of congruence to talk about any kind of figure. So we really have this idea that two figures are congruent if they have the same size and shape, if somehow we can essentially cut one out and put it on top of the other one and make them match up. Okay, so we will need to show that this is consistent with our early definitions, but that's mostly what that theorem up there does. And so the old definitions, we're talking about having equal measures of angles or lengths of line segments. And the new definition talks about isometries mapping. Okay, now let's do some overview here. It turns out that there are actually 5 types of isometries, and only 5. Okay, and this is a really informal definitions of them here. The identity transformation is the boring one. That's where everything's left alone, but it is a type of isometry. A translation, where you basically just slide a figure around. Okay. A reflection, that's a mirror image over a line. A rotation, spinning a center point by some rotational angle. Or a glide reflection, a translation followed by a reflection. So it turns out that every isometry has to be exactly one of those 5 types. A couple other results that we eventually will get, kind of giving away a lot of the good punchlines right here at the beginning, Every isometry can be generated by the composition of a series of 3 or fewer reflections. Okay? And so what we're going to do is we're going to study each of these in detail. It's not really need to study the identity transformation, but we'll talk about translations, reflections, rotations, and glide reflections. And what will we do with each of these? Each of these will start by showing how to do compass and straight edge constructions of the transformations. Okay, well, we'll start by defining these geometrically. Okay, and we will then show how to uh, do compass and straight edge constructions of the transformations, either by hand, by a physical compass and straight edge, or by corresponding tools in either GeoGebra or Geometry Sketchpad. And we'll discuss some tracing paper and paper folding methods. We'll place the figures on a rectangular coordinate grid and use the grid to perform transformations. We'll use a coordinate system to relate the concepts to algebraic expressions. We'll also investigate GeoGebra and Geometry Sketchpad commands for these transformations. And finally, we'll see how we can represent these transformations using matrices. That'll be coming at the end, and view them as elements of algebraic groups and vector spaces. So that's the more advanced stuff at the very end of the chapter. But the rest of these will kind of go through this pattern of going through all of these for each type of transformation. So in the next video, we're going to start looking at these one at a time, and we'll start with translations in the next video.